Everyone, this is the second part of the discussion. I know the previous part was interrupted. uh, Certainly it was interrupted, but okay, fine, let's start with a new class. And in our today's class we will in our previous class actually we just know about the center of mass, why we need a center of mass, how it actually we actually know about this, we knew about the center of gravity, center of buoyancy, but we just generalized that things and we create a new concept of center of mass. And from today, from this class we actually do some kind of calculation. We will do some kind of calculation, mathematical approach, and we actually will find the position of the center of mass, and then we will find the motion of the center of mass. Okay, so let's start. As I just mentioned that, so we already have two definitions of center of mass. One is, it is a point about which the total mass of the object is equally distributed, and the second one is, this is a point, this is a point about which the moment of mass of the object is zero. And the third definition, and the third and most important definition, is that this is a point inside the object. This is a point, maybe this is a point where you, if you just concentrated all the mass of the object, that means this is a point where you actually concentrating the total mass of the object, then the moment of mass about some external point of the whole object and this point mass will be same. That means just let me explain. Now this is the point of rotation. Now this is the origin and it is the point of rotation. We have two body system, that means we only have two objects. That is, one is m1, that is at a distance r1 from this center, that is the origin. So this is the r1 is your position vector of the m1 and r2 is the positional vector of m2. Okay, now if we find the moment of mass about this origin of these two objects, okay, then okay, so that moment of mass should be same, okay, should be same to the moment of mass of the center of mass. Okay, so now this m1 is at a distance r1, so that is at a distance r1 from the origin, and m2 is at a distance r2 from the origin. Let we just, so that means we only have two objects, m1 and m2. Now if you consider the center of mass is here, that is at a distance rcm. Okay, now if you just concentrated these objects here, that means concentrated to a point. That means you just take this m1 and m2, just put them together and just compress them in a point mass and put here. So here we have a m1 plus m2 mass, but it is a point mass. Okay, so now these two things together, they together got some amount of momentum mass about this center, and just replace two things with a point mass of mass m1 plus m2 at here, and find out the momentum mass of this point mass about this axis. So you will get, okay, you will get the same amount of momentum mass. Now do some kind of calculation, it will be clear. Now this m1 has a distance from the axis of rotation is r1, so it will have a momentum mass of m1 r1. Now this m2 has the distance from axis of rotation is r2, that it will have a momentum mass about the origin is m2 r2. So the total momentum mass of the system will be m1 r1 plus m2 r2. Now what will we do? We will replace this system we will replace this system with a point mass, and that point mass will be that point mass will be made by compressing these two objects. Okay, so that means this point mass is made by compressing these two objects. So that means this point mass has a mass m1 plus m2. Now you have to just keep in mind that we don't have this m1 and m2 individually. So we just replace these two things, we just take these two things out, and we just uh, take a point mass here which has a mass m1 plus m2. Now we just want to find the center of mass, sorry, we just want to find the moment of mass of this point mass, and that will be, now take a assumption that this point is at a distance rcm from the axis of rotation. Now this point mass will have a moment of mass will be m1 plus m2 into rcm. Okay, mass into distance from the axis of rotation. Now concept of center of mass is that this point mass should be placed at such a point such that this center of this moment of mass of this point mass must be equal to the moment of mass of the system. Okay, so that means this m1 r1 plus m2 r2 must be equal to m1 plus m2 rcm. So from there we can find this rcm, and it will be your m1 r1 plus m2 r2 by m1 plus m2. Okay, so now thing is that I just repeat this thing. So this is the so that means, so what is the center of mass? That is the third definition. Actually we are going through this, that means we are just stating this as the first, though I have mentioned it is at third. So and this what that says actually the center of mass is a point where you if you where that is a point where if you concentrated all of the mass of the object, then the moment of mass about the center of the moment of mass of the center of mass about the axis of rotation will be same to the moment of mass of the whole body. That means if you assume that this your whole system is the point mass, then the position of the point mass should be such that the moment of mass of that point mass must be equal to the moment of mass of the whole system. That we exactly do the same here. Okay, now that is your definition of RCM. It is m1 r1 plus m2 r2 by m1 plus m2, and you have to keep in mind this RCM is the exact position of the center of mass. That means it is actually position of the center of mass from the origin. Okay, now this RCM can have three components, like any kind of vector, any r vector can have the three components, x I cap, y j cap, and z k cap. So from here we can find the okay. So now we can simplify these things. This RCM equals to your we just do the calculation for the two body problem, but if you have the many body problems, then this RCM will be your m1 r1 plus m2 r2 plus m3 r3 plus m4 r4 and so on by divided by m1 plus m2 plus m3 per m4. Now if we can write this thing as the summation of I equals to 1 over n. That means we have total n number of particles, so we are doing this summation starting from 1 to n, mi ri divided by summation of I equals to 1 to n mi. Okay, that thing is just summation of masses, so that is the summation of mi, and this is summation of m into r, so that is mi ri, summation of mi ri, and we will do the summation over the total number of particles, that is your I equals to 1 to n. Okay, and so this term will give you the total mass of the system. So that will be your total M, capital M, that means this is your total cap mass. So that will be your 1 by m summation of I equals to 1 to n MIRI. Okay, so this is the thing. Now your RCM has three components. One is XCM, YCM and ZCM, and your RI is actually again has three components: XI, YI, ZI. So if you put this thing here and if you put these things here, you will get XCM I cap plus YCM J cap ZCM K cap 1 by a capital M summation of I equals to 1 to n MI XI I cap YI J cap ZI K cap. Now just compare the coefficient of I cap. Left side it is XCM and right side it is 1 by m summation of I equals to 1 to n MI XI. Just do the multiplication here. So that will be MI XI, MI YI, MI ZI. So that means your coefficient of I cap will be MI XI and there is a 1 by m here. So that means your XCM will be 1 by m summation of I equals to 1 to n MI XI, and your YCM will be similarly like that, and similarly that will be, and summation is as I just mentioned, as I already mentioned, that the summation thing is not that much easier. So we will convert that thing into integration, and that XCM will be 1 by m integration of x of dm. 1 YCM will be 1 by m integration of y of dm, and ZCM will be integration of 1 by m z of dm. Now that's the thing. Now as I mentioned, the moment of the moment of mass about the center of mass is 0. That was my second definition. The moment of mass about the center of mass 0, and that we just want to find here. We're just going to prove here. Now let's start with the two body problem, that is M1, that is M2. M1 is at a position R1, position vector R1, that means here, and M2 at a distance R2 from this here, that means the positional vector of the M2 is R2, and the center of mass is here, let it has a position vector RCM. Okay, now center of mass and M1, the distance between them is R1, and the vector R1, sorry, this is R1 prime. Okay, sorry, this is R1 prime. So this is your R1 prime vector, and the center of mass and the M2 are at a distance R2 prime, and this distance is from center of mass is directed in this direction, that is R2 prime. Okay, now if you want to find the moment of mass about the center of mass, then your M1 is at a distance R1 from the center of mass. So that means the moment of mass of about the center of mass will be of M1 will be M1 R1 prime, and your M2 is at a distance R2 prime from the center of mass, and for the M2 the moment of mass about the center of mass will be mass into distance, that is M2 into R2 prime. Then total moment of mass will be M1 R1 prime plus M2 R2 prime. Okay, now just check this thing. This RCM and R1 prime are in the same order. Okay, because RCM ends here and R1 prime starts here, end here, and this R1 vector is taken in the opposite order. So we can write this RCM plus R1 prime equals to R1 from the law of vector addition. Now similarly, this RCM and R2 prime in the same order, but R2 is taken in opposite order. So RCM plus R2 prime is again R2. So R1 prime can be written as R1 prime can be written as R1 minus RCM, and R2 prime can be written as R2 minus RCM. So just put here M1 R1 minus RCM and M2 into R2 minus RCM. Okay, just rearrange these things, M1 R1 plus M2 R2 minus M1 plus M2 RCM. Now from the definition of RCM, that is M1 R1 plus M2 R2 by M1 plus M2, just put here M1 plus M2 will cancel, and then let check that M1 R1 plus M2 R2 minus M1 R1 plus M2 R2, so that will give you 0. Okay, so that is the confirmation of our second definition, that says the moment of mass about the center of mass is 0. Okay, now let's find now we have the position of the center of mass. Now find the velocity of the center of mass. Your position of the center of mass RCM is 1 by m M1 R1 M2 R2. plus m1 m3 r3. Now VCM, what will you have the value of VCM? That will be ddt of RCM. So ddt of 1 by m, this thing, so this thing. Now your 1 by m is constant, so just take it out. So you have to differentiate these things with respect to t. So this m1 is constant, so you will get dr1 dt. Your m2 is constant, you will get dr2 dt only. M3 is constant, you will get dr3 dt only. Okay. So now this r1 is a position of the first mass m1. So dr1 dt will be the velocity of the m1 mass 1. r2 is the position vector of the second of mass, and dr2 dt will be the velocity of the second mass. So that will be your m1 v1 plus m2 v2 plus m3 v3. Just check this thing. Exactly, we get the same things. VCM is your 1 by capital M, that was taken outside of the differentiation, and this m1 v1 plus m2 v2 plus m3 v3. Okay, so similar formula like RCM, VCM will be 1 by m summation of I equals to 1 to n mi vi. Okay, if you want to find the acceleration, just differentiate this VCM with respect to t, you will get the same things, ddt of 1 by m m1 v1 plus m2 v2 plus m3 v3. This value of the VCM I have put here. Okay, so 1 by m can be taken out of the differentiation since it is constant. Now just m1 is again constant, just you have to differentiate v1, m2 is again constant, you have to differentiate v2, and m3 is again constant, you have to differentiate v3. So m1 dv1 dt plus m2 dv2 vt and m3 dv3 vt. This is your acceleration of the first mass, that is a1. This is acceleration of second mass a2. This is acceleration of third mass. So ACM will be 1 by m m1 a1 plus m2 a2 plus m3 a3. So ACM will be 1 by m summation of I equals to 1 to n mi ai. This has the same definition, same formula like the RCM. Okay, now confirmation of Newton's laws of motion. Now what we need, we just take the concept of center of mass just to replace this number of particles with a single point mass. Okay, now you have a diffused body. If you have number of point masses, now with that huge number of point masses, you will have a huge number of component of forces that is very much difficult to handle. So the main concept the main aim of us was to we have to make this thing simple. So to make this simple, we take the concept of center of mass. So center of mass is a point. If you can easily replace your whole body with the center of mass, and you can do the similar type of calculation, but we have to ensure that the formulas those are applicable on the body is also applicable if you take the concept of center of mass. That means if you replace the whole body with a point of mass at the center of mass. So the main formula that we use to calculate any kind of motion of the object is the Newton's law. So from the acceleration of center of mass, we can write that is ACM, acceleration of the center of mass, is your 1 by m of m1 a1 plus m2 a2 plus m3 a3. Now m1 a1 is the force on the mass 1. Okay, m2 a2 is the force on mass 2, m3 a3 is the force on mass 3, f3. So that is 1 by n f1 plus f2 plus f3. Now f1 plus f2 plus f3 is your total force on the object, that is f. Okay, so f by m equals to ACM, so f equals to m into ACM. So that means total force can be written as mass multiplied by the acceleration of the center of mass. That means if you assume this whole mass is concentrated at the center of mass, then your motion will completely described. Your motion can be described completely. Okay, there will not be any lag. Okay, so that is the thing. So Newton's laws of motion is also applicable for the concept of center of mass. So that is all about the center of mass. Okay, so thank you very much.